What if the universe is hiding its biggest secret right in front of us, not in the distant glimmer of stars or the swirling dance of galaxies, but in the empty spaces between them, where an invisible force is silently rewriting the rules of reality? Scientists call it dark energy, and it makes up a staggering 68% of everything in existence. Yet, despite its overwhelming presence, we still don't know what it truly is. This isn't just a gap in our knowledge, it's a cosmic-sized question mark hanging over the very fabric of space and time. Picture this: the universe isn't just expanding, it's accelerating, as if some unseen hand is pressing down on the cosmic gas pedal. Galaxies are racing away from each other faster and faster, defying gravity's pull in a way that baffles physicists. Why? Because dark energy isn't just another piece of the puzzle, it's the force tearing the puzzle apart. It challenges everything we thought we knew about existence, from the birth of the cosmos in the cosmic microwave background to its ultimate fate billions of years from now. But here's what's truly mind-blowing. Dark energy isn't just a distant curiosity. It's a key to unlocking the deepest mysteries of reality. What if it's not just stretching the universe but reshaping our understanding of physics itself? Could it hint at hidden dimensions, new forces, or even a universe far stranger than we've dared to imagine? In this journey, we'll peel back the layers of dark energy theories, from the bizarre to the revolutionary, and explore how they force us to rethink not just the cosmos but our place within it. Buckle up, by the end, you might never look at the night sky the same way again. In 1998, the universe handed scientists a bombshell. Two teams of astronomers were observing distant supernovae, exploding stars so bright they can outshine entire galaxies, expecting to measure how fast the cosmos was slowing down. After all, gravity should have been pulling everything back together since the Big Bang. But the data told a different story. Instead of slowing, the universe was speeding up, its expansion accelerating as if some invisible force was pushing it apart. The shockwaves from this discovery rippled through the scientific community, earning the researchers the Nobel Prize and rewriting the textbooks overnight. This wasn't just a small tweak to physics, it was a revolution. For centuries, gravity had reigned as the dominant force shaping the cosmos, from planets orbiting stars to galaxies clustering together. But here was proof that something else, something far stranger, was at work. Scientists called it dark energy, a placeholder name for the mysterious phenomenon defying explanation. Imagine throwing a ball into the air, only to watch it shoot faster into the sky instead of falling back down. That's the level of cosmic weirdness we're dealing with. The implications were profound. If dark energy was strong enough to overpower gravity on the grandest scales, it meant our understanding of the universe was fundamentally incomplete. Physicists scrambled to reconcile this with Einstein's theory of relativity, dusting off an old idea he'd once called his biggest blunder, the cosmological constant, a mathematical fudge factor representing energy woven into space itself. Suddenly, that blunder didn't seem so foolish after all. But here's the catch: even Einstein's revived concept couldn't fully explain the staggering amount of dark energy detected. The numbers were off by a factor of 10 to the power of 120, the worst mismatch in the history of science. What made this discovery even more extraordinary was how it reshaped our cosmic timeline. For decades, astronomers had assumed the universe would either expand forever at a steady pace or eventually collapse in a big crunch. Dark energy introduced a third, more dramatic fate, a runaway expansion where galaxies would vanish over the horizon, leaving future civilizations with a sky nearly empty of stars. It's a humbling reminder that the universe still holds cards close to its chest, and that the biggest breakthroughs often come from the questions we never thought to ask. Einstein once scribbled a single term into his equations that would haunt him for decades, a mathematical adjustment so small it barely seemed worth mentioning. He called it the cosmological constant, a subtle repulsive force woven into the fabric of space itself, designed to keep the universe static and unchanging. At the time, the prevailing belief was that the cosmos was eternal and unmoving, so Einstein tweaked his theory of general relativity to match that assumption. But when Edwin Hubble discovered the universe was actually expanding in 1929, Einstein famously dismissed his own idea as his greatest blunder, scrubbing the constant from his equations with a mix of embarrassment and frustration. Yet history has a way of playing tricks on us. Nearly 70 years later, when astronomers uncovered dark energy's runaway expansion, they realized Einstein's so-called mistake might have been a stroke of accidental genius. That discarded term, the cosmological constant, suddenly became the leading candidate to explain the mysterious force pushing galaxies apart. The irony was almost poetic. The very idea Einstein had thrown away now held the key to one of cosmology's greatest puzzles. But here's where things get even stranger. While the cosmological constant fits some observations, it's far from a perfect solution. Einstein imagined it as a fixed, gentle pressure balancing gravity. Dark energy, on the other hand, behaves like a runaway train growing stronger as the universe expands. Even more baffling is the sheer scale of the mismatch. Quantum theory predicts the cosmological constant should be unimaginably large, while observations show it's incredibly tiny, off by a factor of 1 followed by 120 zeros. It's like expecting an ocean and finding a single drop of water instead. This leaves physicists in a tantalizing dilemma. Was Einstein right for the wrong reasons, or is dark energy something even more exotic? Some theorists argue the constant might be just one piece of a larger puzzle, a sign of undiscovered physics like extra dimensions or a new fundamental force. Others suggest the vacuum of space itself might be bubbling with fleeting particles that generate repulsive energy. The wildest proposals even speculate that dark energy could change over time, meaning the fate of the universe isn't just expansion but transformation. What's clear is this: Einstein's blunder wasn't a failure of intuition, but a reminder that the universe refuses to be boxed in by human expectations. His cosmological constant, once a footnote in the story of gravity, has become a beacon guiding us toward deeper mysteries. And if history is any judge, the next breakthrough might come from another idea we've underestimated or haven't even imagined yet. If you could peer into the fabric of empty space with a microscope powerful enough to see the quantum realm, you wouldn't find stillness, you'd witness chaos. A frothing sea of particles flickering in and out of existence, appearing and vanishing so fast they barely leave a trace. This is the quantum vacuum, where nothingness is anything but empty. And some scientists believe this frenetic activity might hold the key to dark energy's mystery. Here's how it works according to quantum field theory. Even in a perfect vacuum, pairs of virtual particles constantly emerge, particle and antiparticle twins borrowing energy from the universe for the briefest instant before annihilating each other. These fleeting disturbances create a background energy permeating all of space, like static hissing on an untuned radio. At first glance, this seems like a perfect candidate for dark energy. After all, if space itself crackles with intrinsic energy, couldn't that be what's driving the universe's expansion? But when physicists crunch the numbers, they hit a wall. The energy density predicted by quantum theory is a mind-boggling 10 to the power of 120 times larger than what we observe dark energy to be. That's a 1 followed by 120 zeros, a discrepancy so vast it's been called the vacuum catastrophe. Imagine calculating the weight of a feather and getting an answer heavier than the entire observable universe. That's the scale of error we're dealing with, This isn't just a minor hiccup in the math. It's a glaring sign that something fundamental is missing from our understanding. One possibility is that unknown quantum effects cancel out most of this vacuum energy, leaving behind only a faint residue, the dark energy we detect. Others suggest the vacuum's energy might fluctuate in ways we haven't accounted for, or that gravity behaves differently at cosmic scales. The wildest theories propose that multiple universes with different vacuum energies exist, and we just happen to live in one where the numbers are strangely small. What makes this puzzle so frustrating and so thrilling is that it pits two of science's most successful theories against each other. Quantum mechanics excels at explaining the tiny world of particles, while general relativity masters the vast cosmos. Yet when it comes to dark energy, their predictions clash violently. Resolving this conflict could require a revolution in physics as profound as Einstein's overthrow of Newtonian gravity. So is the quantum vacuum really the source of dark energy? The answer is we don't know yet, but the very fact that such a basic question remains unanswered shows how much we still have to learn about the universe. Every flicker of a virtual particle, every gap in our equations is a clue waiting to be deciphered, one that might rewrite the rules of reality itself. Ancient philosophers believed everything was made of four elements: earth, air, fire, and water. But what if the universe holds a fifth, far more mysterious ingredient? Enter Quintessence, a theoretical form of dark energy that doesn't just fill space, it dances through it, changing its behavior over cosmic time. Unlike the rigid cosmological constant, which Einstein imagined as a fixed property of the vacuum, Quintessence is alive, evolving alongside the universe itself. The appeal of this idea lies in its ability to solve one of cosmology's most puzzling coincidences. Why is dark energy's density nearly identical to the density of matter in the universe right now? It's an eerie balance, as if the cosmos timed its expansion precisely for our era. A static cosmological constant can't explain this, but Quintessence can. Picture a cosmic seesaw. In the early universe, when matter was densely packed, Quintessence might have been weak, barely noticeable. But as galaxies drifted apart and matter thinned out, this hidden field could have grown stronger, gradually taking control of cosmic expansion. This isn't just poetic speculation. Some models suggest Quintessence could explain subtle irregularities in the universe's expansion rate fluctuations that the cosmological constant struggles to account for. Imagine blowing up a balloon unevenly, with some patches stretching faster than others. Quintessence might create similar cosmic textures, leaving faint fingerprints in the way distant supernovae brighten and fade. Yet for all its elegance, Quintessence comes with its own set of mysteries. What kind of field could behave this way? Some theorists compare it to the inflattened field thought to have powered the Big Bang's explosive infancy, a cosmic cousin with similar elusive properties. Others propose it might interact with dark matter, weaving an invisible web of influence between the universe's two greatest unknowns, the most tantalizing possibility. Quintessence could mean dark energy isn't forever. If it weakens over time, the universe's acceleration might one day stall or even reverse. Alternatively, if it strengthens, we could face a big rip where galaxies, stars, and even atoms are torn apart. Unlike the bleak, inevitable expansion predicted by the cosmological constant, Quintessence offers a universe full of dramatic twists and turns, of course. Proving any of this is another challenge entirely. Detecting Quintessence would require spotting impossibly subtle shifts in the fabric of space, far beyond current technology. But that's the thrill of cosmology. Sometimes the wildest ideas, like a fifth element governing reality, turn out to be the keys we've been missing all along. Somewhere in the vast cosmic timeline, there might be a countdown we can't see, a silent, invisible force growing stronger by the second, inching the universe toward an unthinkable fate. This is phantom energy, dark energy's most extreme and destructive incarnation. Unlike ordinary dark energy, which pushes galaxies apart at a steady pace, phantom energy doesn't play by the rules. It feeds on itself, becoming denser as space expands, like a fire that burns hotter the more oxygen you give it. And if this nightmarish scenario is real, the cosmos could be headed for a finale more violent than anything we've dared to imagine, the Big Rip. Picture the universe as a stretched rubber band. In most dark energy models, that band keeps expanding forever, thinning out but never breaking. Phantom energy turns that metaphor into a horror story. Here, the rubber band doesn't just stretch, it snaps. Billions of years from now, as phantom energy's grip tightens, galaxy clusters would be the first to go, ripped apart as space itself tears at the seams. Next, stars would vanish from each other's skies, their light stretched into oblivion. In the final moments, even atoms, the building blocks of everything we know, would be shredded into disconnected particles, space expanding so fast that not even the glue of the strong nuclear force could hold them together. It's the ultimate cosmic catastrophe, leaving behind a cold, empty void where nothing can ever exist again. What makes this idea so unsettling is that it's not pure fantasy. Certain measurements of the universe's expansion hint that dark energy might indeed be growing stronger, though the evidence is still far from conclusive. The critical factor is something called the equation of state, a number describing how dark energy's density changes over time. If this value dips below -1, phantom energy takes the wheel and the Big Rip becomes inevitable. It's like discovering your car's brakes are failing, but on a universal scale. Yet for all its apocalyptic drama, the Big Rip raises a profound question. Is this really how the story ends? Some theorists argue that phantom energy's extreme behavior might violate fundamental laws of physics, like energy conservation or causality. Others suggest that before the rip reaches its climax, quantum effects or undiscovered forces could kick in, pulling the universe back from the brink. Then there's the eerie coincidence that we're living in the brief cosmic era where this fate is still debatable. A sliver of time when the universe is old enough for life to exist but young enough that its doom isn't yet obvious. Whether the Big Rip is a real threat or just a thought experiment, it forces us to confront how little we truly understand about dark energy. The same mysterious force that's accelerating the universe could, in theory, turn on it with unimaginable ferocity. And that's the heart of cosmology's greatest challenge. The universe doesn't owe us a happy ending. It might not even owe us an ending we can comprehend. But with every observation, every equation, we're peeling back another layer of the mystery, one that might reveal not just the fate of the cosmos, but the hidden rules that govern existence itself. What if the solution to dark energy's puzzle isn't an invisible force at all, but a flaw in our understanding of gravity itself? For over a century, Einstein's theory of general relativity has been the bedrock of cosmology, predicting everything from black holes to gravitational waves with uncanny precision. But what if, on the largest scales, those equations aren't quite right? That's the radical proposition behind modified gravity theories, which suggest we might not need dark energy to explain the universe's accelerating expansion. Instead, gravity could simply work differently than we thought when galaxies are millions of light years apart. Take modified Newtonian dynamics as one provocative example. Proposed in the 1980s to explain why galaxies rotate faster than Newton's laws predict, Mund suggests that gravity weakens less dramatically at extreme distances than classical physics assumes. Imagine a car that mysteriously speeds up when you take your foot off the gas. That's the kind of behavior Mund attempts to explain without invoking unseen matter or energy. Some researchers argue that with careful tweaks, similar adjustments could account for cosmic acceleration, rendering dark energy unnecessary. Then there's FR gravity, a more recent twist on Einstein's framework. Here, the equations of general relativity are rewritten to allow gravity's strength to vary depending on the curvature of spacetime itself. Picture a rubber sheet that changes thickness as you stretch it, sometimes resisting deformation, sometimes amplifying it. In certain configurations, FR models can reproduce the effects we attribute to dark energy, all while keeping the universe's content strictly visible. But these ideas come with major hurdles. For one, modified gravity struggles to explain the bullet cluster, a cosmic collision where gravitational lensing reveals massive amounts of invisible matter separated from visible gas. Dark energy and dark matter neatly account for this. Modified theories often require convoluted fixes. There's also the cosmic microwave background, whose intricate patterns align almost perfectly with standard cosmology's predictions. MUND and its cousins have yet to match this precision without reintroducing hidden components. The debate boils down to a philosophical split. Do we trust our equations so much that we're willing to invent unseen substances to make them work, or do we rewrite the equations themselves? Both paths have risks. Dark energy remains unobserved directly, but tampering with gravity's rules could unravel other well-tested predictions, like the behavior of pulsars or the bending of starlight. Yet the allure of modified gravity persists because it offers something revolutionary, a universe where we're not missing 95% of reality, just misreading its rules. Whether that's a profound insight or a dead end, the very fact that such radical alternatives exist shows how deeply dark energy has shaken physics. And until we find definitive proof, the question stands: is our cosmos filled with invisible energy, or are we the ones who've been seeing gravity wrong all along? Stretching across the sky like a faint, crackling whisper from the dawn of time, the cosmic microwave background is more than just leftover heat from the Big Bang. It's a cosmic fossil, imprinted with secrets about dark energy's invisible hand. This afterglow, cooler than deep space today, carries microscopic ripples, temperature variations as tiny as 1 part in 100,000, that tell a story 13.8 billion years in the making. And hidden within those subtle fluctuations lies a startling revelation. Dark energy wasn't just a latecomer to the universe's expansion. It was shaping the cosmos from the very beginning. Imagine the early universe as a boiling cosmic soup, dense with matter and radiation. As this soup expanded and cooled, gravity tugged at slightly denser regions, pulling matter together to form the seeds of galaxies. But dark energy was already at work, subtly counteracting gravity's pull, slowing the growth of these structures in ways that left faint marks on the CMB. Satellites like Planck and WMAP have spent decades mapping these patterns, creating ultra-precise sky maps where every colored blotch represents a moment when dark energy's influence first flickered to life. The real breakthrough came when scientists compared these ancient imprints to the universe's structure today. The CMB's fluctuations predicted how galaxies should cluster across vast distances, but observations revealed they're spaced farther apart than gravity alone could explain. Like finding a stretched-out fingerprint at a crime scene, this mismatch pointed to dark energy as the culprit, silently pushing galaxies apart over billions of years. Even more astonishing, the CMB's data pegged dark energy's density at nearly 70% of the universe's total energy, a number that aligns perfectly with supernova measurements, creating an eerie cosmic consistency. Yet the CMB doesn't just confirm dark energy's existence, it challenges our assumptions about its nature. Some models predicted the CMB would show signs of dark energy weakening or evolving, but Planck's data suggests it's behaved like Einstein's cosmological constant with remarkable steadfastness. Other theories, like Quintessence, would have left distinct scars in the CMB's polarization pattern, scars we haven't found yet. It's as if the universe left us a perfectly tuned puzzle, daring us to question whether dark energy is simpler than we thought or infinitely more complex. What makes these observations so powerful is their universality. The CMB is the closest thing we have to a cosmic control experiment, a snapshot of the infant universe untouched by later chaos. When its data aligns with supernova, galaxy surveys, and gravitational lensing, it forms a web of evidence too tight to ignore. Dark energy isn't just a placeholder for our ignorance, it's a real, measurable force etched into the fabric of space-time itself. And as future telescopes probe even finer details in the CMB's polarized light, we might finally uncover whether this force has been constant all along, or if the universe is still hiding its next great surprise. Long before galaxies formed, the universe was a seething ocean of plasma, ringing like a bell struck by the Big Bang. Sound waves raced through this primordial soup, compressing matter into dense shells that expanded outward at nearly half the speed of light. Then, as the cosmos cooled, those waves froze in place, leaving behind ghostly ripples in the distribution of matter. Today, we call these imprints baryon acoustic oscillations, and they've become one of our most powerful tools for measuring dark energy's relentless push. Think of these oscillations as cosmic measuring tapes etched into the sky. Each ripple marks a consistent distance about 500 million light-years across that serves as a standard ruler for the universe. By comparing how these patterns appear in nearby galaxies versus those billions of light-years away, astronomers can track how space has stretched over cosmic time. It's like finding identical footprints in mud from different eras. If the older prints seem more squeezed together, you know the ground has expanded. This is where projects like the Dark Energy Spectroscopic Instrument, or DAISY, come in. Mounted on a telescope in Arizona, DAISY 5000 robotic eyes capture light from millions of galaxies, mapping their positions in 3 dimensions with unprecedented precision. Each galaxy's location reveals how those ancient sound waves have been stretched or compressed by dark energy's influence. Early results suggest something intriguing. The universe's expansion might not follow the smooth trajectory predicted by Einstein's cosmological constant. Instead, dark energy could be fluctuating, hinting at phenomena like quintessence or even entirely new physics. What makes baryon acoustic oscillations so valuable is their immunity to cosmic illusions. Unlike supernova, whose brightness can be obscured by dust, or the CMB, which shows only a single snapshot in time, these frozen waves provide a consistent benchmark across billions of years. They've already helped confirm dark energy's dominance starting around 5 billion years ago, and future surveys could reveal whether its strength has changed, a clue critical for predicting the universe's ultimate fate. Yet the most astonishing part, these oscillations were first predicted in the 1960s as a theoretical curiosity. No one imagined they'd become a cornerstone of 21st century cosmology. Now, as telescopes peer deeper into the cosmic web, those long silent sound waves are whispering secrets about the invisible force reshaping reality, proving once again that the universe leaves clues in the last places we think to look. In the vast darkness of space, a certain kind of stellar explosion burns with such reliable brilliance that astronomers call them standard candles, cosmic lighthouses whose unwavering glow can measure the universe itself. Type Ia supernova, the thermonuclear detonations of white dwarf stars, don't just light up galaxies, they illuminate the very fabric of space-time. Here's why: when a white dwarf siphons too much mass from a companion star, it crosses a critical threshold and erupts in a blast so uniform that its peak brightness is nearly identical every time. That predictability is the key. By comparing how bright these supernovae appear from Earth to how bright we know they actually are, scientists can calculate their distance with extraordinary precision, like recognizing a 100-watt light bulb from afar and deducing exactly how far away it must be to seem that dim. The year 1998 turned cosmology upside down because of these cosmic explosions. 2 independent teams, the Supernova Cosmology Project and the High Z Supernova Searcher, were scouring the heavens for distant Type Ia supernova, expecting to confirm that the universe's expansion was slowing under gravity's pull. Instead, they found the opposite. Supernova billions of light-years away were fainter than they should have been, meaning space had stretched more than anyone predicted. The universe wasn't just expanding, it was accelerating, as if some invisible force was shoving galaxies apart faster and faster. The discovery was so shocking that team leaders Saul Perlmutter, Brian Schmidt, and Adam Rees would later share a Nobel Prize for their work, while physicists scrambled to explain the anomaly we now call dark energy. But the story doesn't end there. Today, projects like the Dark Energy Survey and the upcoming Vera-C Rubin Observatory are pushing supernova measurements to new extremes, capturing explosions so distant their light has traveled for over 10 billion years. Each one is a time capsule, revealing how dark energy's influence has changed or stayed eerily consistent across cosmic history. There's even a tantalizing hint in recent data. Some supernovas suggest dark energy might not be perfectly uniform, with slight variations in acceleration that could point toward exotic theories like quintessence. Yet supernova aren't flawless tools. Interstellar dust can dim their light, mimicking the effects of acceleration. To compensate, astronomers now analyze the supernova's colors and spectra, filtering out false signals with techniques far more sophisticated than those used in the 1990s. It's a reminder that even the universe's most dependable markers sometimes need decoding, and that the greatest discoveries often come from questioning what we think we know. What makes Type Ia supernova truly extraordinary isn't just their role in uncovering dark energy. It's their dual nature as both destroyers and revealers. A single explosion can outshine a galaxy, yet in its death throes, it gifts us the means to measure existence itself. Every new supernova spotted is another piece of the puzzle, another chance to ask, if the universe's expansion keeps surprising us, what else might we have gotten wrong? The universe has a speed limit problem, and it's throwing cosmology into chaos. For over a century, astronomers have relied on the Hubble constant, a single number representing how fast the cosmos expands. But here's the catch: depending on how you measure it, you get wildly different answers. Study the cosmic microwave background, and you'll calculate one value. Track distant supernova or baryon acoustic oscillations, and you'll land on another. The gap between these results isn't some minor rounding error. It's a stubborn discrepancy of about 10%, persisting despite decades of sharper observations and better instruments. Scientists call this the Hubble Tension, and it's more than just a technical hiccup. It's a potential crack in the foundation of modern cosmology, hinting that dark energy might be playing tricks we don't yet understand. At the heart of the tension lies a cosmic detective story with two conflicting sets of clues. The first comes from the early universe, imprinted in the CMB's faint glow. Planck satellite data, combined with the standard model of cosmology, suggests an expansion rate of roughly 67 kilometers per second per megaparsec. But when astronomers measure the present-day universe using pulsating stars called Cepheids or Type Ia supernova, the rate jumps to 73. That difference might sound small, but over cosmic distances, it adds up fast, like two clocks ticking at slightly different speeds, destined to drift hopelessly out of sync. So where does dark energy fit in? If its strength has changed over time, say, growing stronger or weaker than Einstein's cosmological constant predicts, that could explain the mismatch. Imagine blowing up a balloon in bursts, sometimes fast, sometimes slow. The average rate might not match the current speed. Some theorists propose that dark energy underwent a phase transition billions of years ago, subtly altering the universe's expansion history. Others suggest it might interact with dark matter, creating a dynamic push and pull that skews our measurements. The wildest ideas even speculate that dark energy could be linked to undiscovered particles or fields that temporarily kicked the cosmos into a higher gear. Yet not everyone's convinced the tension points to new physics. Skeptics argue it might stem from overlooked errors like miscalibrations in stellar distances or unaccounted for dust-dimming supernova. Others propose that the early universe contained exotic ingredients like primordial magnetic fields or extra neutrino types that skewed the CMB's snapshot. Then there's the unsettling possibility that both camps are right, and the discrepancy reveals a flaw in how we connect the universe's infancy to its present state. What makes this debate so electrifying is what's at stake. If the Hubble tension holds, it could mean our standard cosmological model, the brilliantly successful framework explaining everything from the Big Bang to galaxy formation, is incomplete. Confirming evolving dark energy would rewrite textbooks, forcing us to rethink not just the universe's fate, but its very construction. On the other hand, if it's merely a measurement glitch, the hunt for an explanation has already driven unprecedented innovation in observational techniques, from gravitational wave astronomy to next-generation space telescopes. One thing's certain, the Hubble tension isn't just a problem to solve, it's an opportunity. Whether it uncovers new layers of dark energy's mystery or exposes hidden biases in our tools, the pursuit is stretching cosmology to its limits. And in that stretch, we might just find the next great leap in understanding the cosmos. Imagine the universe as a cosmic tug of war, with two invisible giants pulling reality in opposite directions. On one side, dark matter, the universe's hidden scaffolding, uses its gravitational grip to gather galaxies into clusters and weave the vast cosmic web. On the other, dark energy stretches the very fabric of space, pushing galaxies apart with a force that grows stronger over time. Together, they dominate the cosmos, making up 95% of everything that exists, yet we've never directly seen either. The key to understanding this shadowy duo lies in their opposing roles. Dark matter acts like cosmic glue. Its gravity binds galaxies together, preventing stars from flying off into the void. Without it, spiral galaxies like the Milky Way would tear themselves apart as they spin. We know it's there because we can see its gravitational fingerprints, the way it bends light around galaxy clusters or speeds up the orbits of stars at the edges of galaxies. It's the universe's unseen architect shaping structure on the grandest scales. Dark energy, meanwhile, is the ultimate cosmic anarchist. Where dark matter builds, dark energy destroys, or at least disperses. It doesn't clump or cluster, it's perfectly smooth, permeating every cubic inch of space with equal intensity. Unlike gravity, which weakens with distance, dark energy's repulsive push grows stronger as the universe expands, creating a feedback loop that accelerates the cosmos toward an ever more distant future. Here's where things get truly fascinating. These two forces might be more connected than we think. Some theories suggest dark energy could be a property of dark matter itself, a hidden interaction that only reveals itself over cosmic time. Others propose that both are manifestations of a deeper, undiscovered physics, like quantum fields we haven't yet detected. There's even speculation that dark matter particles could decay into dark energy, slowly transforming the universe's structure into an ever-expanding void. The irony is palpable. For centuries, we believed the universe was made of stars, planets, and gas, the stuff we could see and touch. Now we know that all of that accounts for less than 5% of existence. The rest is a double mystery, a pair of cosmic ghosts shaping reality from the shadows, and solving one might just hold the key to unraveling the other. If we can pinpoint dark matter's identity in lab experiments, we might uncover clues about dark energy's origins. Or if we finally measure how dark energy changes over time, it could rewrite our understanding of dark matter's role. This isn't just academic curiosity. The fate of the universe hinges on this invisible duel. Will dark energy's push eventually overcome dark matter's pull, leaving galaxies stranded in an endless void? Or does dark matter hold secrets that could alter dark energy's trajectory? The answers lie in the darkness, waiting to be brought into the light. The fate of the universe hinges on a silent, invisible force we're only beginning to understand, and the possibilities are as breathtaking as they are terrifying. Picture a cosmic hourglass, its sand slowly draining toward one of three extraordinary endings, each dictated by dark energy's hidden nature. The first and most haunting is the heat death, a slow fade into eternal stillness. As dark energy accelerates expansion, galaxies will retreat beyond the visible horizon, their light stretched into oblivion. Star formation will sputter out as gas clouds grow too diffuse to collapse. Even black holes, the last bastions of cosmic activity, will evaporate over incomprehensible timescales, leaving behind a vast, lukewarm void where nothing happens forever. It's not an explosion or a collapse, but a whisper, the universe exhaling its final breath into absolute equilibrium. Yet heat death isn't the only option. If dark energy is phantom energy growing stronger as space expands, the universe could meet a far more violent demise, the Big Rip. Here, expansion doesn't just isolate galaxies, it shreds them. First, galaxy clusters would be torn apart, then individual galaxies, then stars and planets. In the final moments, even atoms would be ripped to pieces, space itself stretching faster than the forces holding matter together. Time would lose all meaning as the cosmos fractures into a sea of disconnected particles, each hurled into solitary darkness. This isn't just an ending, it's annihilation on a scale so vast it defies metaphor. But what if dark energy holds a surprise? Some theories suggest it might decay over time, transforming into something entirely new. Imagine a universe where dark energy's repulsive push weakens, allowing gravity to regain control. Matter could collapse back in a big crunch, reversing the Big Bang in a fiery implosion. Even stranger, this collapse might trigger a rebound, a cosmic bounce birthing a new universe with different physical laws. It's the ultimate second chance, a phoenix rising from the ashes of our own spacetime. The wildest possibility, dark energy could be a portal to something beyond our current physics. String theory proposes that our universe is one brain floating in a higher dimensional space. If dark energy destabilizes this brain, we might collide with another universe or dissolve into the bulk of higher dimensions. It's a reminder that the universe's fate isn't just about endings, but transformations we can't yet fathom. What makes these scenarios so profound isn't just their scale, it's their implications for meaning itself. In a heat death, all information, all structure dissolves into noise. A big rip leaves no trace that anything ever existed, but a cyclical universe. That offers the tantalizing possibility of legacy, of cosmic memory echoing across eons. The truth may lie beyond our current grasp, but every observation, every equation brings us closer to answering the ultimate question. Are we witnessing the universe's final act or merely its first? What if dark energy isn't a fundamental law of physics, but a cosmic roll of the dice? This provocative idea comes from string theory, a framework that paints reality as a symphony of tiny, vibrating strings. Among its many radical propositions is the notion that our universe might be just one bubble in an infinite froth of multiverses, each with its own random set of physical constants. In this vast cosmic lottery, dark energy's perplexingly small value could simply be a fluke, a number that landed in the narrow range allowing galaxies, stars, and ultimately life to exist. At the heart of this idea lies the string theory landscape, a mathematical terrain of staggering scale. Calculations suggest there could be 10 to the power of 500 possible vacuum states, distinct configurations of spacetime, each with different properties like particle masses or dark energy density. Most of these universes would be barren, some with dark energy so strong that matter is ripped apart before atoms form. others so weak that gravity crushes everything into black holes. But a vanishingly small fraction, by sheer chance, would have conditions like ours. It's the ultimate anthropic reasoning. We find ourselves in a universe that permits observers because, well, we couldn't exist anywhere else. The implications are as profound as they are unsettling. If true, dark energy's mystery isn't a puzzle to solve, it's a selection effect, a cosmic survivorship bias. No deeper principle dictates its value, it's simply the card we drew. Some physicists embrace this as a pragmatic answer to the "why so small" question. Others recoil, arguing it surrenders too easily, replacing scientific explanation with statistical happenstance. Nobel laureate Steven Weinberg once used this logic to predict dark energy's density before it was measured, an eerie success that still divides the field. But the multiverse hypothesis isn't just about physics, it reshapes philosophy. If countless universes exist unseen, does that diminish our universe's significance or make life's existence against impossible odds even more extraordinary? And how do we test such an idea when other universes might lie forever beyond our observational reach? Some theorists hunt for subtle signatures, collisions between our universe and others that might leave bruises in the cosmic microwave background. Others propose that the very nature of quantum probabilities hints at branching realities. Critics counter that a theory explaining everything risks explaining nothing. Without falsifiable predictions, they argue, the multiverse veers into metaphysics. Yet supporters retort that rejecting it outright might be closing the door on the most elegant solution to multiple cosmic coincidences. Not just dark energy, but the fine-tuned constants enabling chemistry, planets, and life itself. Whether the multiverse is a profound truth or a philosophical stopgap, it forces us to confront the limits of our cosmic perspective. If dark energy truly is random, then the ultimate lesson might be humility, a reminder that even the laws we consider universal could be local bylaws in a reality vaster than our imagination can grasp. And that, in itself, is a revelation worth grappling with. There's something eerily precise about dark energy's grip on the cosmos. Its density sits in a razor-thin sweet spot, strong enough to keep the universe from collapsing under gravity's pull, yet weak enough to allow galaxies, stars, and planets to form. Nudge it slightly higher, and space would have expanded too rapidly after the Big Bang for matter to clump together. Tweak it lower, and gravity would have crushed everything back into a fiery singularity long before life could emerge. This isn't just a minor curiosity, it's a cosmic tightrope walk, and the fact that we're here to ponder it raises a profound question. Is this perfect balance a stroke of luck or something deeper? One way to make sense of this fine-tuning is the anthropic principle, the idea that the universe's fundamental constants must align with the conditions necessary for observers like us to exist. In other words, we shouldn't be surprised to find ourselves in a universe where dark energy is just right, because we couldn't exist in one where it wasn't. It's like a puddle marveling at how perfectly its hole fits its shape, unaware that the hole came first. This reasoning can feel unsatisfying, even circular, but it's hard to dismiss when faced with the sheer unlikelihood of our universe's delicate equilibrium. Yet the anthropic principle doesn't stand alone. For some, it's a stepping stone to an even wilder possibility, the multiverse. If countless universes exist, each with randomly dialed values for dark energy, gravity, and other constants, then it's inevitable that at least one would land in the habitable zone. We just happen to be in that lucky one. This isn't science fiction. String theory and inflationary cosmology both suggest mechanisms that could spawn such a cosmic ensemble. The catch: if every possible universe exists, the multiverse doesn't explain why dark energy has its specific value. It merely shifts the question to why we find ourselves in this particular slice of reality. Critics argue this approach borders on giving up. If we invoke an infinite array of unobservable universes to explain fine-tuning, have we traded scientific rigor for metaphysical speculation? Some physicists counter with a pragmatic defense. The multiverse might be the only framework that naturally accounts for dark energy's value without resorting to unexplained coincidences or untestable design. After all, science has a history of expanding our cosmic perspective. From one solar system to billions of galaxies, why not take the next leap? But there's another angle. What if dark energy's fine-tuning isn't accidental at all? Could it reflect an underlying law or symmetry we haven't yet uncovered? Some theorists propose that dark energy's value might be fixed by a deeper principle, like quantum vacuum energy cancelling out to near zero through some hidden mechanism. Others explore dynamical models where dark energy self-adjusts over time, naturally settling into life-friendly parameters. These ideas are speculative, but they keep the door open to a universe where fine-tuning isn't just a fluke, it's a clue. The debate ultimately forces us to confront the limits of our knowledge. Is the universe fine-tuned because it's one of many, or because it's the only possible way for complexity and consciousness to arise? Or is the very question a mirage, a side effect of our human tendency to see purpose in probability? Whatever the answer, dark energy's Goldilocks value isn't just a puzzle for cosmologists. It's a mirror reflecting our deepest hopes and fears about whether reality is random, inevitable, or something stranger than we've dared to dream. Could the force driving the universe apart be seeping in from dimensions beyond our own? This mind-bending possibility comes from braneworld cosmology, a radical reimagining of reality where our three-dimensional universe floats like a sheet of paper in a higher dimensional space. In this framework, dark energy might not be a mysterious substance at all, but the gravitational tug of war between our brain and hidden dimensions just out of reach. Picture our universe as a soap bubble suspended in a vast, frothy ocean of higher dimensions. According to string theory, these extra dimensions curled up so tightly we can't perceive them, could influence our cosmos through gravity alone. While particles like light and matter are stuck to our brain, gravity might leak into the bulk, the multidimensional space between brains. This leakage could explain why gravity feels so weak compared to other forces. Most of its strength dissipates into dimensions we can't see. But here's the twist, that same leakage might be fueling cosmic acceleration. As gravity drains from our brain, it could create an effective repulsive force, mimicking what we call dark energy. The most famous version of this idea comes from the Randall-Sundrum model, which proposes two brains separated by a warped fifth dimension. In this setup, the geometry of the extra dimension acts like a cosmic funhouse mirror, amplifying tiny energy differences into observable effects. One variation suggests our brain might be slowly drifting toward another hidden brain, with the interaction between them generating dark energy's push. Others propose that quantum fluctuations in the bulk create ripples that nudge our universe apart from within. What makes braneworld theories so compelling is their economy. Instead of inventing a new quantum field or particle to explain dark energy, they repurpose gravity's behavior in higher dimensions, a concept already baked into string theory. They also offer potential solutions to other cosmic puzzles, like why the vacuum energy is so small compared to predictions. If gravity's leakage cancels out part of the vacuum's energy density, it could leave behind just the faint residue we observe as dark energy. Yet challenges remain. No experiment has detected extra dimensions directly, and some braneworld predictions conflict with precise measurements of gravitational waves. There's also the lingering question of why we perceive exactly three spatial dimensions if others exist. Still, the possibility that dark energy is a shadow cast by unseen dimensions adds thrilling depth to the mystery. It suggests we're not just missing pieces of the cosmic puzzle, we might be missing entire dimensions of the board. Whether this hypothesis holds up or not, it stretches our imagination beyond the familiar confines of space-time. The notion that dark energy could be a side effect of gravity's multidimensional dance reminds us that the universe's greatest secrets might not be hidden in distant galaxies, but in the invisible architecture of reality itself. What if dark energy isn't the constant force we've assumed it to be? Imagine it as a cosmic chameleon shifting its strength over billions of years, subtly altering the universe's expansion in ways we're only beginning to detect. This isn't just a wild speculation, it's a serious possibility that could rewrite our understanding of cosmic history. Some theories propose that dark energy was far more influential in the universe's infancy, playing a hidden role in the explosive period of inflation just moments after the Big Bang. Others suggest it might have pulsed weakly during the cosmic dark ages, leaving faint fingerprints on how galaxies eventually clustered together. The clues lie in the delicate balance of the universe's expansion rate. If dark energy's push has varied over time, it would leave distinct markers in the way galaxies are distributed across the cosmos. Surveys like the Dark Energy Spectroscopic Instrument are already hunting for these subtle patterns, mapping millions of galaxies to trace how dark energy's influence has evolved. Even more telling could be the cosmic microwave background's polarization, the afterglow of the Big Bang, which might carry imprints of early dark energy's fleeting presence. But why does this idea matter? If dark energy isn't constant, it could mean the universe's fate isn't set in stone. A weakening dark energy might allow gravity to regain dominance, leading to a future where expansion slows or even reverses. Conversely, if it's growing stronger, the Big Rip, a catastrophic tearing apart of space itself, becomes more likely. The implications stretch beyond cosmology, touching the very nature of reality. Could dark energy be tied to undiscovered particles or fields that evolve over cosmic time? Might it interact with dark matter in ways we haven't yet imagined? Future telescopes like the European Space Agency's Euclid or NASA's Nancy Grace Roman Space Telescope aim to settle the debate. By measuring the universe's expansion with unprecedented precision, they could catch dark energy in the act of changing, revealing whether it's a steady force or a dynamic player in the cosmic drama. Either way, the answer will force us to rethink not just the universe's future, but its past. And that's the beauty of cosmology. The deeper we look, the more we realize how much we've yet to discover. What if everything we think we know about dark energy is just a trick of cosmic geography? Picture this: instead of a universe uniformly filled with dark energy, Earth sits inside a vast, nearly empty bubble, a region of space where matter is sparser than the cosmic average. From our vantage point, galaxies outside this void would appear to be racing away faster than expected, not because space itself is accelerating, but because we're looking out from a low-gravity neighborhood. This is the void hypothesis, a radical alternative to dark energy that suggests the universe's expansion might not be what it seems. The idea isn't as far-fetched as it sounds. If our local cosmos were a cosmic desert, less dense than surrounding regions' gravity's weaker pull, here would make distant galaxies seem to recede faster, mimicking the effects of dark energy. Think of it like standing in a valley and seeing mountains in the distance appear to slope upward more steeply than they really do. Your perspective distorts the true landscape. Similarly, a void hundreds of millions of light-years wide could warp our measurements of cosmic expansion, fooling us into inferring an invisible repulsive force. But here's the catch: a void large enough to explain the data would be staggeringly improbable. Standard cosmology predicts that matter should be distributed fairly evenly across the universe, with only minor fluctuations. For us to occupy such an enormous underdense region would be like winning a lottery with odds of 1 in a billion. Even stranger, the cosmic microwave background. The afterglow of the Big Bang shows near-perfect uniformity, with no signs of a void vast enough to account for the apparent acceleration. Yet some theorists aren't ready to dismiss the idea entirely. Sophisticated models propose that a void wouldn't need to be completely empty, just slightly less dense than average, to subtly skew our observations. Others suggest that exotic physics, like faster-than-light expansion in the early universe, could have carved out such a bubble naturally. The most compelling counterargument, though, comes from supernova data. If we lived in a void, distant supernova should appear brighter than expected, not dimmer as dark energy predicts. Observations consistently favor the latter, leaving the void hypothesis on shaky ground. What makes this debate so fascinating isn't just the science, it's the philosophical tension between two worldviews. Do we live in a special place that deceives us, or is dark energy a universal truth? Most evidence points to the latter, but the void scenario remains a tantalizing reminder that our cosmic perspective is always limited. After all, the universe has fooled us before. Centuries ago, we thought Earth was the center of everything. Today, we might be making the same mistake on a grander scale. The difference now, we have the tools to question our assumptions and the humility to know we might still be wrong. Dark energy isn't just a cosmic mystery, it's a glaring spotlight on the deepest fracture in modern physics. For decades, quantum mechanics and general relativity have operated as separate kingdoms, each ruling its own domain with unmatched precision. The tiny world of atoms obeys quantum laws, while the vast cosmos dances to gravity's tune. But dark energy forces these two realms to collide, revealing a fundamental incompatibility at the heart of reality. If we're ever going to crack this puzzle, we'll need a theory that bridges the divide, a framework where gravity and quantum physics aren't rivals but partners. Enter quantum gravity, the grand quest to unify these seemingly irreconcilable worlds. One of the most daring approaches is loop quantum gravity, which reimagines space-time itself as a fabric woven from tiny, indivisible threads. Picture the universe as a cosmic tapestry, where each thread is a quantum loop carrying the smallest possible unit of area or volume. Unlike the smooth continuum of Einstein's relativity, this framework suggests space is pixelated, a digital cosmos where not even time flows continuously. The thrilling implication: dark energy could emerge from the gaps between these quantum stitches, like tension in a stretched weave. Some models even propose that loop quantum gravity naturally cancels out the vacuum energy predicted by quantum field theory, leaving behind just the faint repulsion we call dark energy. It's a tantalizing hint that spacetime's quantum structure might hold the key to the universe's accelerating expansion. Then there's holography, a radical idea born from black hole physics. The holographic principle suggests that all the information in a volume of space can be encoded on its boundary, like a three-dimensional movie projected from a two-dimensional screen. Applied to cosmology, this could mean dark energy isn't a force within space but a shadow cast by quantum interactions at the universe's edge. Imagine the cosmos as a colossal quantum computer, with dark energy as the energy cost of running its cosmic code. This perspective flips the problem on its head. Instead of asking what dark energy is, we might need to ask what the universe is computing. String theory offers another angle, proposing that dark energy could arise from hidden dimensions curled into microscopic shapes. In some versions, the energy driving cosmic acceleration might be the vibration of higher dimensional branes colliding or resonating in ways we can't directly observe. Others suggest dark energy is tied to the landscape of possible universes in string theory's vast mathematical terrain, a multiversal echo of our particular cosmic luck. Yet for all their brilliance, these theories share a common challenge: testing them. Quantum gravity operates at scales so small and energies so high that direct experiments are currently impossible. That's where dark energy becomes more than a mystery, it's a potential Rosetta Stone. By studying how dark energy behaves across billions of years, we might spot subtle deviations from Einstein's predictions that reveal quantum gravity's fingerprints. Future telescopes could uncover whether dark energy's strength changes over time or if its effects ripple unevenly through space, clues pointing to the underlying quantum nature of spacetime itself. What makes this pursuit so electrifying isn't just the promise of solving dark energy's riddle. It's the chance to rewrite physics from the ground up, stitching together a theory where the quantum and cosmic realms finally speak the same language. Whether through loops, holograms, or strings, the answer won't just explain why the universe is accelerating. It could reveal the hidden code that shapes reality itself. Could the universe be thinking? It sounds like science fiction, but some daring theories propose a connection between dark energy and consciousness, an idea that blurs the line between physics and philosophy. At first glance, the notion seems absurd. Dark energy is a cosmic force measured through galaxies' motions, while consciousness arises from neurons firing in brains. Yet beneath the surface, both share an eerie commonality. They're fundamental mysteries that resist conventional explanation. Could there be a deeper link, or is this just poetic speculation? One provocative theory comes from the intersection of quantum physics and information science. If reality at its smallest scales behaves like a network of interconnected data, a concept called it from bit, then dark energy might not be a force at all, but a byproduct of cosmic information processing. Picture the universe as a vast quantum computer, with every particle interaction performing a calculation. Dark energy, in this view, could represent the energy cost of running the program, the computational overhead of maintaining spacetime itself. It's a wild idea, but not entirely without precedent. Even black holes, according to modern physics, encode information on their surfaces like cosmic hard drives. Why couldn't the universe as a whole operate on similar principles? Then there's panpsychism, the philosophical stance that consciousness isn't unique to brains but a fundamental feature of reality. Some interpretations suggest dark energy could be the physical manifestation of a rudimentary cosmic awareness, not in the sense of a thinking entity, but as a pervasive proto-consciousness woven into spacetime's fabric. Think of it like the universe's background hum, a faint glimmer of subjectivity accompanying existence itself. While mainstream science dismisses this as untestable metaphysics, it raises a fascinating question. If consciousness emerges from complex systems like brains, could the most complex system of all, the universe, host some form of it? Critics argue these ideas cross into pseudoscience, and they're not wrong. No experiment has ever detected cosmic consciousness, nor does any equation require it. Yet history shows that today's heresy sometimes becomes tomorrow's breakthrough. Quantum entanglement seemed mystical until lab tests proved it real. The Big Bang Theory was once ridiculed as religious creationism in disguise. The line between profound insight and poetic nonsense is often drawn in hindsight. What makes these speculations valuable isn't their likelihood, but their ability to stretch our thinking. Dark energy defies every intuitive framework we have. Maybe the solution requires perspectives we haven't yet imagined, ones that bridge the cold equations of physics with the warm complexities of mind. Whether that bridge exists remains unknown, but the act of searching reminds us that the universe's greatest mysteries aren't just out there in the void. They're woven into the very act of questioning itself. The hunt for dark energy is about to enter its most thrilling chapter yet. Across the globe, teams of scientists are preparing to launch a new generation of telescopes and satellites designed to pry open the universe's best-kept secret. At the forefront is the European Space Agency's Euclid mission, a spacecraft equipped with a razor-sharp eye capable of mapping the three-dimensional positions of billions of galaxies across 10 billion years of cosmic history. Unlike past surveys, Euclid won't just catalog where galaxies are. It will trace how their distributions have been stretched and warped by dark energy's invisible hand, searching for subtle distortions in spacetime itself. Then there's the Vera-C, Rubin Observatory's legacy survey of space and time, or LSST, poised to revolutionize ground-based astronomy. Perched atop a Chilean mountain, its 8.4-meter mirror will scan the entire southern sky every few nights, capturing time-lapse movies of the cosmos on an unprecedented scale. By tracking how supernovae brighten and fade across vast distances and measuring the clustering of galaxies with pinpoint accuracy, LSST could detect whether dark energy's strength has changed over time, a smoking gun for theories like Quintessence. The telescope's 3,200-megapixel camera, the largest ever built, will photograph the sky with such depth that a single image could contain millions of galaxies, each a data point in the puzzle. NASA's Nancy Grace Roman Space Telescope, set to launch later this decade, takes a different approach. Dubbed the Mother of Hubble, Roman will combine Hubble's crystal-clear vision with a field of view 100 times wider, allowing it to survey the cosmos at breakneck speed. Its primary target, the bending of light around massive galaxy clusters, a phenomenon called weak gravitational lensing. By mapping how dark energy alters these cosmic magnifying glasses over time, Roman could reveal whether the force interacts with dark matter, or if it's even more exotic than we've imagined. But the real game-changer might come from combining these missions. Imagine Euclid's precision galaxy maps cross-referenced with LSST time domain fireworks and Roman's lensing data, creating a multi-messenger portrait of dark energy's influence. Together, they could measure the universe's expansion history with a precision of 1%, squeezing the errors in our models until discrepancies like the Hubble tension either resolve or explode into full-blown crises for physics. The stakes couldn't be higher. If these experiments confirm dark energy is truly constant, it might validate Einstein's cosmological constant, leaving us to grapple with its bizarrely fine-tuned value. But if they find evidence of evolution, it could ignite a revolution pointing toward dynamical fields, extra dimensions, or physics beyond Einstein. Either way, the data pouring in over the next decade won't just fill textbooks, it could rewrite them. And for the first time in history, we'll have the tools to move from speculation to certainty, turning the universe's greatest mystery into its greatest revelation. Imagine building a universe from scratch, not with stars and galaxies, but with lines of code and mathematical equations. That's exactly what cosmologists do when they harness the raw power of supercomputers to simulate dark energy's influence on the cosmos. These aren't just fancy video games, they're precision laboratories where scientists can rewind time, tweak fundamental laws, and watch virtual universes evolve under different dark energy scenarios. The goal, to see which models match the real universe we observe, and which ones collapse under the weight of their own contradictions. One of the most ambitious of these projects is the Millennium Simulation, a virtual cosmos spanning billions of light years, where dark energy's push is encoded into the very fabric of the simulation's spacetime. Starting with the faint density fluctuations imprinted in the cosmic microwave background, researchers let gravity and dark energy duke it out over cosmic epochs, watching as virtual galaxies form, cluster, and drift apart. The results are stunningly detailed, a digital tapestry of filaments and voids that eerily resemble the real cosmic web. But here's the catch: when simulations assume dark energy behaves like Einstein's cosmological constant, they produce galaxies that match our telescope's observations almost perfectly. Tweak the parameters, though, and the virtual universe veers into uncanny valleys where galaxies are too clustered, too sparse, or too young to match reality. These simulations aren't just passive experiments, they're discovery engines. In 2017, a team running the Illustris TNG simulation noticed something bizarre. When they dialed up dark energy's strength to mimic phantom energy, their virtual galaxies didn't just drift apart, their shapes distorted, as if space itself was stretching them into cosmic taffy. It was a hint that if dark energy grows stronger over time, future astronomers might not just see galaxies receding, they'd see them physically warping. Another simulation, called Bahamas, revealed how dark energy subtly alters the way galaxy clusters grow, leaving a faint statistical fingerprint in their masses, a prediction later confirmed by real-world observations. But the real power of these simulations lies in their ability to test the untestable. Want to see what happens if dark energy suddenly vanishes 5 billion years from now? Or if it oscillates like a cosmic pendulum? Supercomputers can model these impossible scenarios in weeks, offering glimpses into alternate cosmic destinies. Some of the most intriguing results come from simulations where dark energy interacts with dark matter, a possibility most theories dismiss. In these runs, dark energy's push can sculpt dark matter halos into unusual shapes or even strip them away entirely, effects that, if detected in real galaxy surveys, could rewrite the rules of cosmology. Of course, virtual universes have limits. Even the most advanced simulations can't capture every atom, star, or black hole. They rely on approximations and shortcuts to make the computations feasible. And there's always the risk of garbage in, garbage out. If a simulation's assumptions are flawed, its predictions will be too. That's why the best simulations are constantly refined, their code polished by comparing their output to newer, sharper telescope data in a feedback loop of discovery. What's next? Projects like the Dark Energy Spectroscopic Instrument are feeding their colossal datasets back into simulations, creating a virtuous cycle where real observations train virtual universes, and virtual universes suggest new places to point telescopes. Future exascale supercomputers, capable of quintillions of calculations per second, promise simulations so detailed they'll track individual stars within galaxies, all while modeling dark energy's cosmic dance with unprecedented precision. In the end, these digital cosmos are more than just tools, they're mirrors, reflecting our best theories back at us with brutal honesty. When a simulation fails to match reality, it's not just a glitch, it's a clue that our understanding of dark energy might be missing a crucial piece. And when one succeeds, it's a quiet triumph, a sign that somewhere in the labyrinth of equations and code, we're glimpsing the universe's hidden blueprint. The cosmos is drowning in data, billions of galaxies mapped across billions of light years, each a pixel in the universe's grand portrait. For human astronomers, passing this deluge is like drinking from a fire hose. But where our brains hit their limits, artificial intelligence thrives. Machine learning algorithms trained on simulations and real observations are now scouring the heavens for dark energy's fingerprints, spotting patterns too subtle or complex for even the sharpest human eyes. Take galaxy surveys, where AI doesn't just count stars, it reads the cosmic tea leaves. By analyzing the shapes and distributions of millions of galaxies, neural networks can detect how dark energy warps the large-scale structure of the universe, revealing distortions invisible to traditional statistics. One breakthrough came when researchers fed AI data from the Dark Energy Survey, a project imaging 300 million galaxies. The algorithm flagged peculiar clustering patterns in the cosmic web, slight overdensities and voids that matched predictions of how dark energy would stretch space-time over eons. These weren't random flukes, they were the statistical whispers of an invisible force, teased out by machine learning's ability to process nonlinear relationships no human equation could capture. Another team trained an AI on simulated universes with varying dark energy strengths, then set it loose on real quasar data. The result, the AI independently inferred the universe's expansion rate with startling accuracy, corroborating and sometimes challenging human-derived measurements. But the real game changer is how AI handles the cosmic microwave background. The CMB's temperature fluctuations are famously subtle, with variations smaller than 1 part in 100,000. Traditional analysis methods average these fluctuations across large patches, potentially washing out crucial details. Machine learning, though, can analyze the CMB's raw pixel data, hunting for non-Gaussian signatures, tiny asymmetries that might betray dark energy's influence in the universe's first moments. In 2022, a deep learning model analyzing Planck satellite data identified anomalous hot and cold spots aligned in ways that defied standard inflationary models. Some theorists now speculate these could be scars from early dark energy's brief dominance, a hypothesis humans might have missed without AI's pattern-spotting prowess. The synergy between AI and cosmology goes beyond mere number crunching. Generative adversarial networks, or GAN, are creating hyper-realistic simulated universes to test dark energy theories at unprecedented scales. Unlike traditional simulations, which take months to run, these AI models can generate plausible cosmic structures in hours, letting researchers play "what if" with dark energy's parameters, strengthening it here, weakening it there, to see which versions produce galaxies matching our own. Meanwhile, reinforcement learning algorithms are optimizing telescope observation schedules, ensuring every second of precious instrument time is spent hunting dark energy's most elusive signals. Yet for all its power, AI isn't a magic bullet. These systems are only as good as their training data, and if that data carries biases, say, from incomplete simulations or instrumental noise, the AI can amplify those errors. There's also the black box problem. When a neural network spots a novel pattern, it doesn't explain why. A human scientist still has to interpret the result, bridging the gap between correlation and causation. That's why the future isn't AI replacing cosmologists, but AI and cosmologists working in tandem, machines to sift the haystacks, humans to understand the needles they find. As next-generation telescopes like the Vera-C, Rubin Observatory come online, generating petabytes of data nightly, AI will be the unsung hero in the dark energy hunt. It's a partnership as vast as the cosmos itself, human curiosity guiding machine intelligence, together unraveling the universe's deepest secret, one algorithm at a time. Dark energy isn't anti-gravity, it's something far stranger. One of the most persistent myths is that this mysterious force simply repels matter like some cosmic magnet pushing galaxies apart. But the truth is more nuanced. Dark energy doesn't tug on objects the way gravity does. It's woven into the fabric of space itself, stretching the universe from within. Picture a loaf of raisin bread baking in the oven. As the dough expands, the raisin's galaxies don't move through the dough, they're carried apart because the space between them grows. That's dark energy's signature effect, not a force acting on the cosmos, but a property of the cosmos, accelerating expansion without directly interacting with matter at all. Then there's the claim that dark energy is just a measurement glitch, a cosmic mirage caused by faulty instruments or incomplete data. Skeptics point to discrepancies in supernova brightness or quirks in galactic surveys as proof that the acceleration might be an illusion. But here's the reality: dark energy isn't inferred from a single observation. It's the consistent thread tying together multiple, independent lines of evidence. The cosmic microwave background's temperature fluctuations, the clustering of galaxies across billions of light years, even the way massive objects bend light, all converge on the same conclusion. When results from Planck, Daisy, and Hubble all point in the same direction, the odds of a systematic error shrink to near zero, another common misconception. That dark energy is new or recently discovered. While the term entered the spotlight in the late 1990s, the concept has roots stretching back to Einstein's cosmological constant in 1917. The difference is that today, we're not theorizing, we're observing its effects in real time. Modern telescopes have caught dark energy red-handed, watching as distant supernovae recede faster than classical physics predicts. This isn't a placeholder for ignorance, it's a measurable phenomenon with tangible consequences for the universe's structure. Perhaps the most tempting myth is that dark energy will lead to an imminent cosmic doomsday. Headlines love to speculate about the big rip or sudden vacuum decay, but the truth is far less dramatic. Current data suggests dark energy's influence is weak and steady, a slow burn rather than an explosion. Even if it's phantom energy, the most extreme variant, any catastrophic tearing apart of space-time wouldn't occur for tens of billions of years. The universe, it seems, is in no rush to meet its end. What scientists do agree on is that dark energy represents a frontier, not a dead end. It's not a fully understood force, but it's also not a guess. Every new telescope, every supercomputer simulation, every AI-analyzed dataset brings us closer to cracking its code. The myths, they're just speed bumps on the road to discovery, distractions to be dispelled as we focus on the real mystery. Why our universe refuses to play by the rules we thought we knew. The vastness of the cosmos has always humbled humanity, but dark energy adds a chilling new dimension to that humility. If the universe is accelerating toward infinite expansion, if galaxies will eventually vanish beyond an unreachable horizon, leaving our Milky Way an isolated island in an ever-darkening void, does that render human existence meaningless? Philosophers and scientists have wrestled with this question since the discovery of cosmic acceleration, and the answers are as profound as they are unsettling. Consider the timeline. In 1 trillion years, the last stars will flicker out. In 10 to the power of 100 years, even black holes will evaporate. The universe will be a featureless sea of expanding space, devoid of structure, memory, or change. Against this backdrop, the few thousand years of human civilization seem vanishingly brief, a spark in an endless night. Some argue this cosmic perspective reduces all human achievement to futility. Why create art, pursue science, or build civilizations if everything is destined for oblivion? But here's the counterpoint. Significance isn't measured by duration alone. A symphony isn't worthless because it ends, nor is a sunset less beautiful because it fades. The fact that we're here at all, that atoms forged in dying stars assembled into beings capable of pondering the universe's fate, is statistically miraculous. Dark energy doesn't erase that wonder, it sharpens it. The accelerating cosmos forces us to confront an uncomfortable truth. Meaning isn't handed down by the universe. It's something we create right here, right now, in defiance of the void. The irony is rich. Dark energy, a force that stretches space itself, also stretches our understanding of purpose. Ancient cultures found meaning in celestial cycles, seasons repeating, stars returning. Modern cosmology offers no such comfort. Instead, it gifts us something rarer, the awareness that our moment matters precisely because it's fleeting. The projects we undertake, the knowledge we gather, the connections we forge, these aren't footnotes to cosmic indifference. They're rebellions against it. Perhaps the most radical response to dark energy's existential challenge comes from futurists who refuse to accept heat death as inevitable. Concepts like Boltzmann brains or quantum resurrection are speculative, but they reveal a timeless human impulse to imagine survival against impossible odds. Whether through far future technology or theoretical physics, the drive to outlast the cosmos may be the ultimate expression of meaning-making. In the end, dark energy doesn't dictate our significance, it reveals how fiercely we insist on having it. The universe may not care about us, but that's irrelevant. We care, and in a cosmos racing toward dissipation, that stubborn act of caring might be the most meaningful thing there is. The discovery of dark energy didn't just reshape cosmology, it reignited an ancient conversation about the boundaries between science and spirituality. For some, the universe's eerie fine-tuning dark energy's delicate balance allowing galaxies, stars, and life to exist hints at intentional design. Theologians and scientists alike have marveled at the so-called Goldilocks principle. If dark energy were slightly stronger, galaxies would never form, slightly weaker, and the universe would have collapsed long ago. This precision has led some to argue for a cosmic architect, a perspective that bridges mathematical elegance with metaphysical wonder. The late physicist Freeman Dyson once mused that the universe appears unexpectedly hospitable to life, an observation that resonates deeply with those who see science and faith as complementary lenses on reality. Yet for others, dark energy is a natural phenomenon demanding no divine explanation. The multiverse theory, for instance, posits that countless universes exist with random physical constants. Ours simply happens to be one where dark energy's value permits complexity. In this view, what seems like fine-tuning is just statistical inevitability. We couldn't observe a universe that didn't allow observers. Prominent scientists like Steven Weinberg have framed this as a sobering counter to design arguments, suggesting dark energy's value reflects nothing more than cosmic luck. The debate isn't just academic, it cuts to the core of how we assign meaning to scientific discovery. Does dark energy's mystery invite awe, or is it merely a puzzle waiting for a material solution? Religious traditions have responded to dark energy in strikingly different ways. Some Judeo-Christian thinkers align it with concepts of a sustaining divine presence, echoing passages like Colossians 1:17, which speaks of a force holding all things together. Hindu cosmology, with its cyclical universes and dynamic balances, finds parallels in theories of dark energy's evolving strength. Meanwhile, Buddhist philosophies often interpret it through impermanence and interdependence, a reminder that even space-time is subject to change. These interpretations aren't uniform. Within every faith, there are voices cautioning against conflating scientific models with sacred texts. As Jesuit astronomer Brother Guy Consolmagno notes, science tells us how the heavens go, faith tells us how to go to heaven. The friction arises when either side oversteps. History is littered with examples of religion resisting scientific progress, from Galileo's trial to the rejection of evolution. But the inverse also occurs, scientists dismissing spiritual perspectives as inherently irrational. Dark energy challenges this dichotomy. Its sheer strangeness, a force dominating the cosmos yet invisible to our senses, defies simplistic categorization. Even secular physicists like Marcelo Gleiser argue that science and spirituality address fundamentally different questions. One explores mechanisms, the other meaning. Perhaps the most productive middle ground is found in the language of mystery itself. Dark energy, like consciousness or the origins of the universe, occupies a frontier where empirical data and existential questions intersect. Theologian John Polkinghorne, a physicist turned Anglican priest, framed such mysteries as signals of transcendence, a phenomena that science describes but cannot fully explain away. This isn't a call to invoke the supernatural prematurely, but an acknowledgement that some discoveries expand our humility rather than our certainty. What makes dark energy uniquely compelling in this dialogue is its dual role as both a measurable force and a cosmic riddle. It doesn't merely push galaxies apart, it stretches the boundaries of how we reconcile empirical observation with human yearning for purpose. Whether one sees it as a clue to a deeper order or a challenge to traditional beliefs, its presence in the cosmos demands something rare in modern discourse, a willingness to hold multiple truths at once. After all, the same universe that runs on equations we can write also inspires questions we can't. Investing billions in dark energy research might seem like chasing cosmic ghosts until you realize how profoundly this pursuit tangles with our daily lives. The technologies born from peering into the void have a habit of circling back to Earth, revolutionizing medicine, computing, and even your smartphone. Take the charge-coupled device, or CCD, the light-sensitive chip that transformed digital imaging. Originally developed for telescopes to capture faint starlight, it now powers everything from medical X-rays to smartphone cameras. The same adaptive optics used to correct atmospheric blur in ground-based observatories now sharpen vision for patients undergoing laser eye surgery. Even the algorithms that map the cosmic web inspire more efficient routes for delivery trucks and power grids. When we fund the outer edges of human curiosity, we're not just buying data about distant galaxies, we're seeding innovations that ripple through society in ways no one can predict. But the returns aren't just technological. Dark energy research is a mirror held up to our deepest existential questions. For all its abstractness, this field forces us to confront what it means to exist in a universe governed by forces we can't see or touch. The same tools measuring galactic redshifts also refine our understanding of quantum mechanics and relativity, the frameworks underlying GPS satellites, nuclear energy, and future fusion reactors. By probing why the universe accelerates, we're stress-testing the very laws that make modern technology possible. It's like reverse engineering reality's source code, with each breakthrough revealing new rules we can harness. Critics argue this knowledge has no cash value, but history disagrees. The discovery of electromagnetism once seemed like academic whimsy until it birthed the electrical grid. Quantum mechanics was dismissed as theoretical play until it gave us transistors and the digital age. Dark energy sits at a similar crossroads. Today's useless equations about spacetime's expansion could unlock tomorrow's warp drives or energy breakthroughs. When the Hubble Space Telescope's flawed mirror was repaired, the techniques developed spawned precision manufacturing methods now used in semiconductor factories worldwide. The line between abstract and applied science has always been porous and often invisible until decades later. Beyond practicality, there's an intangible return on investment perspective. Understanding dark energy reshapes humanity's place in the cosmic story. It humbles us with the realization that we're riding a speck of dust in an accelerating cosmos, yet empowers us with the knowledge that we've decoded so much of its mystery. That duality of insignificance and ingenuity fuels not just science, but art, philosophy, and our collective drive to explore. The billions spent aren't just buying data, they're funding the next chapter of what it means to be human in an ever-expanding universe. And that might be the most valuable ROI of all. Art doesn't just reflect reality, it reimagines it, transforming the unfathomable into something visceral. When scientists grapple with dark energy's abstract equations, artists take up an entirely different challenge, making the invisible felt. Take Raphael Lozano Hemmer's Pulse Spiral, an installation where hundreds of light bulbs flicker in sync with viewers' heartbeats, their collective rhythm evoking the cosmic web's vast, interconnected threads. Here, dark energy's imperceptible push becomes a sensory experience, the ebb and flow of light mimicking the universe's accelerating expansion. Or consider Katie Patterson's Earth, Moon, Earth, a piece where Beethoven's Moonlight Sonata is transmitted to the moon and back, the returned signals fragmented by lunar terrain, a metaphor for how dark energy distorts our understanding, leaving gaps where meaning once seemed clear. Music, too, has wrestled with these themes. Composer John Luther Adams become ocean swells and recedes like cosmic tides, its orchestral waves echoing the tension between gravity's pull and dark energy's push. The piece won a Pulitzer not for explaining physics, but for making listeners feel the vast, impersonal forces shaping existence. Even electronic artists like Holly Herndon use algorithms to generate soundscapes that mimic quantum fluctuations, those virtual particles popping in and out of the vacuum, the same substrate some theorize fuels dark energy. Her track Eternal layers choral vocals with glitching synths, creating an unsettling beauty that mirrors the universe's paradox, sublime order underpinned by unfathomable chaos. Visual artists often literalize the metaphor. Julie Meritu's massive canvases, dense with overlapping lines and smudged geometries, evoke the cosmic web structure, the way dark energy stretches galaxy clusters into filamentary ruins. Her work Epigraph, Damascus looks like a Hubble image filtered through a storm, its chaotic elegance hinting at the violence beneath expansion. Meanwhile, Team Lab's digital installations immerse viewers in swirling particle fields that respond to human touch, collapsing the divide between observer and cosmos. Walk through their universe of water particles and you're not just learning about dark energy, you're inside it, your movements rippling through a simulated space-time. But why does this matter? Because art doesn't just illustrate science, it interrogates it. When filmmaker Christian Marclay created The Clock, a 24-hour montage of timekeeping scenes from cinema, he exposed humanity's obsession with measuring what's ultimately fleeting. Dark energy, in this light, isn't just a physics problem. It's a cultural mirror reflecting our anxiety about time, impermanence, and scale. Similarly, Oliver Eliassen's Weather Project, with its artificial sun hanging in London's Tate Modern, forced visitors to confront their place within larger systems, a microcosm of how dark energy reshapes our cosmic context. The most provocative works blur the line between data and poetry. Dark Matter, a collaborative project by sound artist Bill Fontana and physicist David Kaiser, sonified particle collision data from CERN, turning subatomic chaos into an eerie symphony. Listen closely and you'll hear the statistical noise of the universe's hidden scaffolding, an acoustic glimpse of the unseen. Or consider Trevor Paglen's The Last Pictures, a gold-plated disk of images sent to orbit Earth, destined to outlast humanity. It's a dark energy allegory in miniature, art persisting in the void long after its creators are dust. These creations share a common thread. They don't seek to solve dark energy's mystery. Instead, they embrace its elusiveness, using ambiguity as a creative catalyst. In doing so, they democratize cosmology, inviting the public to engage not with equations, but with emotion and intuition. A child who will never grasp tensor calculus can stand beneath Lozano Hemmer's pulsating lights and sense the universe's heartbeat. That's the alchemy of art. It translates the incomprehensible into a language of wonder, reminding us that some truths are best understood not through logic but through awe. Hollywood loves a good cosmic villain, and dark energy has played the role more than once, just never accurately. Take Marvel's Doctor Strange, where the sorcerer wields dark energy like a glowing green weapon, bending reality with a flick of his wrist. In reality, dark energy doesn't shoot from your fingertips or crackle like lightning. It's not a mystical force, it's a property of empty space, silent and omnipresent. Yet these dramatic liberties reveal something fascinating. When science can't hand filmmakers a tangible explanation, creativity rushes in to fill the void. The Transformers franchise takes the absurdity further, treating dark energy as a literal fuel source. In Revenge of the Fallen, ancient machines harvest it from pyramids to power interstellar travel. Real dark energy doesn't pool beneath monuments or power engines. It's not something you can bottle or weaponize, but the trope persists because it taps into a cultural craving. The idea that the universe's greatest mysteries might be harnessed, controlled, even conquered. It's a seductive fantasy, one that glosses over the humbling truth. Dark energy doesn't care about human ambition. It's the universe's background hum, indifferent to pyramids or superheroes. Even Star Trek, usually meticulous with its technobabble, fudges the details. episodes reference dark energy reactors or dark energy lifeforms, bending the concept to fit interstellar diplomacy plots. The irony, dark energy's actual effect pushing galaxies apart, would make Star Trek's Galactic Federation impossible over time. Starships wouldn't just warp between planets, they'd battle against the very fabric of space accelerating away. But accuracy isn't the point. These stories use dark energy as shorthand for the unknown, a narrative device to evoke wonder or danger. Comics, meanwhile, take even wilder leaps. DC's Darkseid, Lord of Apocalypse, channels the Omega Effect, a cosmic force often conflated with dark energy. His I-beams don't just incinerate, they erase targets from spacetime itself. Scientifically, this is nonsense. Dark energy doesn't selectively annihilate, it uniformly expands, but metaphorically, it's genius. Darkseid's power mirrors humanity's deepest fear, that the universe's expansion isn't just indifferent but actively hostile, unraveling reality piece by piece. The real damage of these portrayals isn't their inaccuracy, it's the missed opportunity. Dark energy's true mystery is more compelling than any superhero plot. Imagine a story where astronauts stranded in deep space watch their home galaxy redshift into nothingness as dark energies grip titans. No villains, no explosions, just the chilling realization that the universe itself is the antagonist. Or a detective thriller where cosmologists race to decode dark energy's secrets before Earth's telescopes are blinded by an accelerating cosmos. The truth doesn't need embellishment to thrill. It just needs to be framed with the same awe that inspired ancient stargazers. Pop culture's greatest service might be its mistakes. Every time a blockbuster botches the science, it sparks questions. Audiences leave theaters Googling, is dark energy real? And that curiosity is a gift. The gap between fiction and fact isn't a flaw, it's a doorway. And once someone steps through, they might just discover that reality, with its runaway universes and quantum vacuums, is stranger than anything Hollywood could dream up. Imagine a classroom where students don't just read about dark energy, they reach out and touch it. That's the power of modern educational tools transforming abstract cosmology into hands-on experiences. At the forefront are interactive simulations like NASA, Universe in a Box, where sliding a simple dial lets kids watch galaxies drift apart faster and faster, visualizing dark energy's push in real time. Or take the Cosmic Voyager app, which shrinks the observable universe into a smartphone screen. Pinch to zoom from the Milky Way to the cosmic microwave background, and the app overlays data from real telescopes, showing how dark energy's fingerprints appear at different scales. These aren't just fancy animations, they're bridges between equations scribbled on whiteboards and the living, expanding cosmos. Planetariums have leveled up too. The Hayden Planetarium's Dark Universe show doesn't just project stars, it immerses audiences in a 3D map of the universe, with beams of light tracing how supernova measurements revealed cosmic acceleration. As the narrator explains dark energy's role, the dome overhead warps and stretches, simulating spacetime's expansion in a way that clicks viscerally. For younger students, programs like The Little Star That Could anthropomorphize galaxies as characters racing away from each other, their voices growing fainter as space expands, a playful metaphor that sticks long after the lights come up. Gamification takes engagement even further. Euclid, Dark Matter Detective, developed with the European Space Agency, turns players into cosmic investigators analyzing simulated galaxy surveys for dark energy's subtle distortions. Meanwhile, Minecraft's Cosmic Craft mod lets students build their own multiverse, tweaking dark energy's strength to see if their virtual cosmos collapses, rip apart, or stabilizes. The most innovative might be Quantum Odyssey, a VR experience where players navigate a spaceship powered by vacuum energy, dodging quantum fluctuations that represent theoretical dark energy candidates. Fail to account for phantom energy's growth, and your ship gets torn apart atom by atom, a visceral lesson in cosmology's stakes. What makes these tools revolutionary isn't just their tech, it's their accessibility. The Dark Energy Explorer kit, used in classrooms from Nairobi to New York, costs less than a textbook. With a flashlight, diffraction grating, and a few filters, students replicate how astronomers measure redshift, watching spectral lines stretch as their universe expands. Even board games like Cosmic Dawn simplify complex ideas. Players draft cards representing dark energy, dark matter, and baryonic matter, competing to build the most stable universe. It's Monopoly meets multiverse theory. The ripple effects are profound. When a high schooler in Brazil used an open-source simulation to model how dark energy alters galaxy clustering, her project won international acclaim, not because she solved the mystery, but because she asked new questions. That's the ultimate goal, equipping the next generation not just with answers, but with the curiosity to challenge them. Because the kid building a Lego model of the cosmic web today might be the physicist who cracks dark energy's code tomorrow. And it all starts with letting them play with the universe. You don't need a PhD to help crack one of cosmology's greatest mysteries, just an internet connection and curiosity. Projects like Galaxy Zoo have revolutionized how science gets done by turning everyday people into cosmic detectives. Here's how it works when telescopes capture millions of galaxy images. Even the most advanced algorithms struggle to categorize their intricate shapes. That's where you come in. By logging onto platforms like Zooniverse, volunteers flip through galaxy snapshots answering simple questions. Is this spiral arms or elliptical? Merging or undisturbed, each classification feeds directly into research papers, with citizen scientists often listed as co-authors. Over 50 published studies now bear the names of amateur contributors who spotted rare galactic oddities that computers missed. The beauty of these projects lies in their democratization of discovery. In 2007, a Dutch schoolteacher named Hanny van Arkel stumbled upon a strange green blob while classifying galaxies on Galaxy Zoo. Dubbed Hanny's Voorwerp, this enigmatic object turned out to be a cosmic ghost, a quasar-lit gas cloud spanning thousands of light years. Professional astronomers had scanned the same data for years without noticing. Similarly, the Green Pea Galaxy's compact, star-forming systems critical for understanding cosmic evolution were first flagged by volunteers noting their peculiar hue. These aren't just feel-good stories, they're proof that pattern recognition, that deeply human skill, still outperforms machines for certain tasks, but galaxy classification is just the beginning. The Dark Energy Surveys, Supernova Hunters project trains volunteers to spot stellar explosions in telescope images, helping measure the universe's expansion rate. For those who prefer hands-on involvement, the Unistellar Network connects backyard astronomers worldwide, pooling observations of distant supernova and variable stars. Even smartphone users can contribute through apps like Gravity Spy, which analyzes data from gravitational wave detectors while teaching users to distinguish cosmic signals from noise. The impact goes beyond data crunching. When the Hubble Space Telescope faced budget cuts, Galaxy Zoo users mobilized, sending thousands of letters to Congress emphasizing public passion for cosmology. This grassroots advocacy helped secure funding, proving that citizen science isn't just about assisting professionals, it's about reshaping who gets to participate in the scientific process. What makes these initiatives so powerful is their scalability. While a single researcher might classify a few hundred galaxies per week, the Galaxy Zoo community processes millions. That volume lets astronomers spot ultra-rare objects and subtle trends invisible in smaller samples. It's like having 50,000 research assistants working in parallel, each bringing fresh eyes to cosmic puzzles. Ready to join the hunt? Head to platforms like Zooniverse or SciStarter, where projects range from identifying gravitational lenses to mapping the Milky Way's dust clouds. No prior knowledge is needed. Training tutorials guide you through every step. Who knows, the next cosmic breakthrough might come from your living room, proving that when it comes to unraveling dark energy secrets, the most powerful instrument isn't a telescope but collective human curiosity. What happens when humanity's reach exceeds its grasp, not just toward the stars, but toward the very fabric of space-time? The idea of manipulating dark energy sounds like science fiction, but as our understanding grows, so does the tantalizing possibility of one day influencing cosmic expansion itself. Imagine a future where advanced civilizations could dial dark energy's strength up or down like a thermostat, slowing the universe's acceleration to keep galaxies within reach, or speeding it up to avoid a hypothetical big crunch. The power to reshape the cosmos carries unimaginable responsibility, forcing us to confront ethical dilemmas that make nuclear ethics look simple by comparison. First, consider the risks of unintended consequences. Dark energy isn't an isolated lever, it's woven into the universe's foundational physics. Tweaking its value could destabilize the cosmic web, altering gravity's delicate balance with expansion in ways we can't predict. A civilization that weakens dark energy too much might trigger gravitational collapse, pulling galaxies into collisions that sterilize entire regions of space. Conversely, amplifying it could accelerate the isolation of galactic clusters, dooming future civilizations to eternal solitude. The stakes are unfathomable. This isn't just playing with fire, it's playing with the furnace that forged reality. Then there's the question of consent. If one species, say, humanity in 1,000,000 years decides to adjust dark energy's parameters, does that infringe on the rights of other civilizations across the cosmos? Unlike environmental policies on Earth, there's no galactic UN to mediate such decisions. Philosophers call this the intergenerational equity problem, scaled to cosmic proportions. Does any civilization have the moral authority to alter universal constants that affect all life, past and present? Even if our descendants develop the technology, they might lack the ethical framework to wield it justly. Yet the most profound dilemma lies in the paradox of survival. If dark energy continues unchecked, the universe faces heat death, a slow, cold demise. Manipulating it could, in theory, stave off that fate, but at what cost? Ethical systems rooted in preservation might argue for intervention, while others could view cosmic entropy as a natural order not to be disrupted. Some theologians and scientists even suggest that dark energy's value isn't arbitrary, it might be a prerequisite for life's existence. Tampering with it could unravel the very conditions that allowed us to evolve in the first place. The wild card: we might not be alone in this debate. If other intelligent species exist, they could be grappling with the same questions, or might have already acted. The absence of obvious cosmic engineering could signal that advanced civilizations universally deem it too dangerous. Alternatively, we might live in a universe where dark energy's value has already been set by predecessors, a chilling thought that turns cosmology into an archaeological dig for cosmic architects. For now, these questions remain hypothetical. We lack both the technology to manipulate dark energy and the physics to even conceive of how it might be done. But history shows that today's impossibilities often become tomorrow's tools. The ethical frameworks we build, now rooted in humility, foresight, and interstellar empathy, might one day guide choices that ripple across billions of years. Until then, dark energy's greatest lesson might be this: some mysteries aren't just puzzles to solve, but boundaries to respect. Biologists peer into the cosmos and see patterns eerily familiar. The branching veins of a leaf mirroring the filamentary structure of the cosmic web, the pulse of a jellyfish echoing the rhythmic flicker of distant quasars. This isn't poetic coincidence, it's a testament to how universal principles shape everything from cells to galaxies. When ecologists study how nutrients flow through ecosystems, they're modeling energy distribution, a framework astrophysicists adapt to trace dark energy's influence on galactic clusters. Take trophic cascades, where removing a top predator ripples through an entire food web. Cosmologists now ask, could dark energies trigger similar chain reactions, destabilizing the delicate balance of galaxy formation in ways we've yet to map? Artists, meanwhile, translate the ineffable into the visceral. Abstract painter Julie Meritou layers maps and astrophysical diagrams beneath her chaotic brushstrokes, creating visual metaphors for dark energy's distortion of spacetime. Her work Epigraph Damascus doesn't just depict expansion, it makes you feel it, the canvas stretching and warping under unseen forces. Sound designers take it further, sonifying data from the Dark Energy Survey into eerie, pulsing soundscapes where rising tones mimic galaxies fleeing beyond the cosmic horizon. These aren't just interpretations, they're experiments in perception, revealing how human senses might grapple with concepts beyond linear logic. The intersection of biology and cosmology yields even wilder hybrids. Biophysicists modeling slime mold growth noticed the organism's tendrils seek optimal pathways strikingly similar to the universe's large-scale structure. When researchers fed the mold simulated dark energy parameters, its growth patterns shifted, hinting that biological systems might encode responses to cosmic forces we barely understand. Meanwhile, computational artists like Rethink Existence train AI on dark energy simulations, generating swirling, luminous visuals that evolve in real time, their algorithms mimicking the universe's own generative rules. Perhaps the most unexpected collaboration lies in neuroscience. When brain scans reveal neural networks firing in fractal patterns akin to galaxy distributions, it raises a provocative question. Could the same mathematical principles governing dark energy's effects also underlie thought itself? Philosophers and physicists alike are exploring whether consciousness and cosmic expansion share a deeper logic, not because the brain is a universe, but because both may emerge from universal optimization laws we're only beginning to discern. These interdisciplinary leaps matter because they break cosmology's echo chamber. When a biologist points out that dark energy's uniform distribution resembles the homeostasis of a living organism, it challenges physicists to consider if the cosmos self-regulates. When a poet describes redshift as the universe forgetting its own language, it reframes entropy in human terms. The best science thrives at these boundaries where rigid methodologies soften and analogies flourish. After all, dark energy didn't reveal itself through equations alone. It took astronomers, philosophers, and even painters to help us see the void for what it truly is. Not emptiness, but the universe's silent architect. Dark energy doesn't just hide in the voids between galaxies, it lingers in the gaps of our understanding, a cosmic question mark that refuses to be ignored. For all our towering equations and gleaming telescopes, we're still peering through a keyhole at a universe that operates on rules we've only begun to glimpse. And that's not a failure, it's the thrill of discovery in its purest form. Every unanswered question about dark energy is an invitation, a challenge flung across the cosmos, daring us to think bigger, dig deeper, and rewrite the textbooks once again. Consider how far we've come. A century ago, astronomers debated whether the Milky Way was the entire universe. Today, we're grappling with forces that stretch spacetime itself, forces so pervasive they dictate the fate of everything. Yet the more we learn, the stranger the puzzle becomes. Dark energy could be the cosmological constant Einstein dismissed, a quantum quirk of the vacuum, or something entirely beyond our current physics, maybe even a sign that we're missing entire dimensions of reality. The beauty is in the possibilities. Each hypothesis, no matter how outlandish, is a thread in a tapestry we're still weaving. This isn't just academic curiosity. Unraveling dark energy secrets could crack open the door to technologies we can't yet imagine. Think of how quantum mechanics, once a baffling theory about subatomic oddities, gave us lasers, MRI, and the silicon chip. Dark energy's solution might one day revolutionize energy, computation, or even our ability to navigate the cosmos. Or it might simply humble us, revealing how much we've overestimated our grasp of the universe. Both outcomes are equally valuable, so as we step back from this journey, remember, the universe isn't obliged to make sense to us. Its mysteries don't exist to be solved on our timeline or in ways that fit neatly into our frameworks. Dark energy is a reminder that wonder isn't found in having all the answers, but in the pursuit of them. Every time a telescope captures a new sliver of the sky, every time a supercomputer simulates another fractal of cosmic expansion, we're not just collecting data, we're having a conversation with the universe itself. Now it's your turn. What do you think dark energy is hiding? A fundamental force, a glitch in gravity's code, or something no one's even dreamed up yet? Drop your theories in the comments, because the next big breakthrough might start with a spark of curiosity from someone just like you. And if this cosmic deep dive left you hungry for more, hit that like button, subscribe, and ring the bell to join us as we keep unraveling the universe's greatest mysteries. The cosmos is full of stories waiting to be told. Let's discover them together.